Hi everyone and welcome back to Matthew Wister. Today we're going to do another chemistry Regents review on chemical equilibrium. So before we actually get into reading the cluster, I want to review what equilibrium is. So equilibrium is whenever we have a reversible reaction, we can identify if we have these two arrows pointing between the reactants and between the products. Now, this arrow represents our forward reaction. The forward reaction is when the reactants are forming the products. But now the reverse rate is when the products are being broken down to form the reactants. So in this reversible reaction, it's typically when we have a closed system where there's going to become a point where the rate of the forward reaction is going to equal the rate of the reverse reaction. So this is called dynamic equilibrium. So the rate of forward reaction equals rate of reverse reaction. Now there is a principle that you need to associate with chemical equilibrium, which is Le Chatelier's principle. Now, what this principle says is that if you apply stress to a system at equilibrium, the system is going to change in order to relieve that stress and reestablish equilibrium. So if you're at equilibrium and it experiences some sort of stress, the system is going to change and reestablish equilibrium again. Now, there are three factors that affect equilibrium, which is concentration, temperature, and pressure, but only for gaseous systems. So concentration refers to when we're adding, more mass, more atoms into either reactants or the products. Temperature is when we're adding heat or taking away heat. And pressure is if we're limiting the space in the closed container or we're giving more space to the closed container. So now let's read the cluster. The production of ammonia is vital for manufacturing fertilizers. If you don't know, ammonia actually involves a reverse reaction. The global chemical industry traditionally relies on the Haber-something process, which establishes a dynamic chemical equilibrium between nitrogen gas, hydrogen gas, and ammonia gas. This reversible reaction is represented by the chemical equation below. So we have nitrogen, hydrogen, ammonia, and energy. Kj is energy in joules. It's also heat. To maximize the yield of NH3 or ammonia, engineers control various factors of the system. Various factors. Chemical engineers working on a sustainable version of this process collected data on the concentration of the reactants and products over time inside a rigid 1.0 liter closed reaction vessel at a constant temperature of 673.15 Kelvin. Their observations are recorded on the table below. So again, we have a closed reaction, so a closed container, and a constant temperature. So now let's see. So we have the concentration of nitrogen, hydrogen, and ammonia. And these are all gases. So if we want to annotate, we can see that at first, none of the concentrations are equal. But after 15 minutes, we can see that the concentrations of hydrogen and ammonia gas, they're staying constant, they're staying the same. So now let's look at the question. Which time interval represents the period during which the reaction system has achieved dynamic chemical equilibrium? So again, equilibrium, all of them are balanced, right? And well, as we noted here, after 15 minutes to 25 minutes, we can see that the concentrations are staying constant. So they've reached a balanced. So that's chemical equilibrium. Question. Based on table 1, which statement correctly identifies the relationship between the rate of the forward reaction, so that's going from reactants to products, and the rate of the reverse reaction, which is from products to reactants, at 20 minutes. So at 20 minutes, we can see that it's balanced. So if we look here, let's see. The rate of the forward reaction is 0 and the rate of the reverse reaction is 0. Well, that's not true because we know that at 20 minutes, the system is in dynamic chemical equilibrium, as we talked about here in the first question. So since it's at chemical equilibrium, that means that the rate of the forward reaction and the reverse reaction are going to be equal to each other. So our answer is going to be C. The rate of the forward reaction is equal to the rate of the reverse reaction. Number 3. State in terms of concentrations the evidence from Table 1 that demonstrates the chemical reaction system has reached dynamic equilibrium. Well, just like we talked about earlier, we can see that when it reaches 15, we can see that during the time interval of 15 to 25 minutes, the concentrations of nitrogen, hydrogen, and ammonia gas stay constant. Question 4. Based on the chemical equation provided, determine the total number of moles of hydrogen that must react completely to produce exactly 6 moles of NH3. Well, I'm just going to rewrite the equation that we had given here. So I'm just going to rewrite that. So I'm just going to write N2 plus 3H reversible 2 NH3 plus 91.8 kJ. So it's asking how many moles of hydrogen do we need in order to have 6 moles of ammonia? Well, based off the given equation, we can make a ratio. So according to this equation, we had 3 moles of hydrogen for every 2 moles of ammonia. But it's asking how much hydrogen do we need for 6 moles of ammonia. So I'm going to put a variable x and then 6 moles of ammonia. So if we think about it, mathematically, for every 2 moles of ammonia, we need 3 moles of hydrogen. So if we were to think about how do I get from 2 to 6, we multiply by 3. So if I do that on that side, I also need to change the other side. So I'm going to multiply the 3 by 3. And I'm going to get x is equal to 9. So that means that I need 9 moles of hydrogen in order to react to completely produce 6 moles of ammonia. Next question. A second group of engineers decides to evaluate how a sudden shift in experimental variables impacts the quantities of substances present at equilibrium. At exactly 30 minutes, additional hydrogen gas is rapidly injected into the closed 1.0 liter reaction vessel while keeping the temperature constant in 673.15 Kelvin. Well, if we're adding more hydrogen gas, that means we're adding more to our reactant side. So let's just keep that in mind. We're adding 2 reactants. Therefore, we're adding stress. We're impacting the system. So we're adding stress to the reactants. So when additional hydrogen is injected into the system at 30 minutes, which statement describes the immediate effect on the rates of the chemical reactions? Well, if we're adding more stress into the reactants, that means that the rate of the forward reaction is going to increase because we have more reactants to produce more products. So that's going to mean that the rate of the forward reaction is increasing. And we can eliminate options C and D because it's not going to remain constant and it's not going to immediately drop to 0. And the rate of the forward reaction, how is it going to decrease? We're adding more reactants, so the reactants are going to work even harder in order to provide or to produce more products. Explain in terms of Le Chatelier's principle why the concentrations of nitrogen decreases after the addition of hydrogen. Well, if I rewrite our equation here, N2, 3H2. So in this case, we're adding hydrogen into the reactant side. And whenever we're adding hydrogen to the reactant side, that means we're adding a stressor. And the stressor is going to cause a disturbance in the equilibrium. And because of that, the system or equilibrium is going to shift to the right side in order to restabilize. And when that happens, that means that the forward reaction is going to be encouraged more. So more reactants are going to form products. So in the reactant side, we also have nitrogen. And the reason why, again, nitrogen is going to decrease is because the forward reaction is causing the reactants to then form more products. So it's going to consume the reactant, nitrogen, to produce more ammonia. Explain in terms of collision theory how an increase in the pressure of the reaction vessel achieved by decreasing its volume would affect the rate of the forward reaction. So we're increasing the pressure of a container. So here we have a container, right? The closed container. Let's say we increase the pressure, so now we have less space, we're decreasing the volume. So now the particles, right, they're hitting each other way more frequently because they have less space to move around. So they're colliding more. And when they collide, it's going to increase the likelihood of the molecules to react with each other. So we have an increased reaction rate or increased forward reaction. Therefore, decreasing the volume is going to increase the concentration of gas particles because now they're more concentrated in this closed space, which is going to lead to an increased frequency of effective collisions between the gas molecules, which then increases the rate of the forward reaction. Find the design of this chemical system to maximize the mass of ammonia produced at equilibrium. Your response must specify a precise modification to either the temperature or pressure conditions of the reaction vessel and explain why the change favors the forward reaction. So again, the forward reaction is what's helping us produce more ammonia because it's when the reactants are forming products. So the question is asking, what change do we need to do to the system in order to increase the amount of products that we're producing? So in this equation, we see that we have a heat in the product side. And whenever we have heat in the product side, that means that heat is being released. So this makes it an exothermic reaction. So if we were to decrease the temperature, we're taking away from the products. And if we take away from the products, the equilibrium is going to shift back to the products because we need to replenish that products. But in order to shift to the products, we need to be producing more products, which favors the forward reaction because the forward reaction is what's getting the reactants to form the products. Therefore, it's going to favor the forward reaction. So since the forward reaction is exothermic, if we reduce the temperature, the system shifts to the products, favoring the forward reaction that produces an increased amount of NH3.